All right, so this one's multiple questions, A, B, C, D, E, maybe a possible free response. So I like to recycle, so here's recycling that graph. The largest intervals from negative infinity to infinity. That just means here as it goes out to the right with the arrow, it goes on forever. And then this one, we're not sure if it actually tapers off towards the x-axis or just goes down to negative infinity. We don't know, but we'll just assume that it's not interrupted anymore beyond negative 5 and 15, what we see here. So the largest intervals, if we start on the left, I'll do it up here where I can see, and then I'll try and bring it down. So it looks like it'll be negative infinity up to the first is negative 2 with a what? Parenthesis or bracket? Parenthesis, right? So even though the function is defined there, remember, it's not defined or continuous at negative 2. And then union will pick up at negative 2, cruise all the way to, we can get all the way to positive 2 with another parenthesis. We'll step over to cruise all the way to 5 with another parenthesis. And then we'll pick up at 5 and cruise all the way to where? 6, yeah. Now, does 6 get a bracket or parenthesis? Bracket, yeah. On that interval, that's a half open interval. The right end point is the same as the limit from the left. From 6, we'll pick up with a parenthesis on the right side and cruise all the way to 8. Another parenthesis, union, 8 to 10, union. Then we go from 10 to 11. And then finally, we get to 11, and we can cruise forevermore after that. So, again, not very difficult, but kind of something new where we can have endpoints loosened up on the 3-point definition, okay, if we look at it on that interval. All right, so that would go down in part A. Let me move that down. All right, part B. These make good multiple-choice questions. Find the largest value of some number B so that our function up above is continuous on the half-open interval from 5 to B inclusive, but not from 5 to B plus 1. Find the largest value so it's continuous from 5 up to B, but not at B plus 1. Anyone know what that number is? Okay, so I want it to be continuous from 5 to B, closed. I want that to work, but I want from 5 to B plus 1. When I try to include the right endpoint now, I want it to fail. 6 would work, right? Let's see. This would be continuous from 5 to 6, right? But if I add 1 to 6, that becomes 7, and then this one actually fails, right? Now, it doesn't fail because of the right endpoint. It would fail because what? As I go from 5 to 7, yeah, there's a jump at 6, so it's not continuous on the open interval. It would actually pass at the right endpoint. So that looks like it would be the largest one, right? So B is equaling 6. That's the largest value. But now it says to find all the values of B that work. Are there other values of B that would work besides 6? Anything between 5 and 6, right. If I replace 6 with 5.5, it would be continuous from 5 to 5.5. That'd be right around here. But as soon as I add 1 to 5.5, it gets me to 6.5. And now, again, it's going to fail because I've crossed the jump. So anything that when I add 1 is going to get me past the jump is going to meet the criteria. So all the values of B that work. Now, I'm going to list this as an inequality. B could equal 6, right? That's the largest it can be. It could be smaller than 6. What's the smallest B could be and still work? Could it be 5? No, if it's 5, it's not an interval. So it could be like 5.00001 though, yeah? Because when you add 1 at 6.001, so we'll just say greater than 5. Okay, so those are all the values of B that work. 5 doesn't work, but if it's anything bigger than 5, when I add 1, it gets me past 6. 6 would be the largest. So it's kind of interesting here that we're talking about intervals, and then we're listing our solutions kind of, we could list it as an interval. The values of B that work are from 5 to 6. So that can get kind of confusing, though, for people, so I typically list them with inequalities. All right, so you're given these sets of criteria. You're trying to make it work. All right, go ahead and do C on your own. Give the smallest value of A so that our function above is continuous on the largest possible interval from A non-inclusive to 10. The largest possible, so it's continuous from A to 10. Kind of goes without saying. If we're finding the smallest value of A, that's going to make the interval from A to 10 the largest possible interval. Anyone got it? 8, right. If we look at it from 8 to 10, notice we're not trying to include the left endpoint. Thank goodness. If we start at 8 right here, it's going to be continuous up to 10. Yeah. So 8 would be the smallest. If I go anywhere to the left of 8, it's going to fail on the open interval. So 8 is definitely the smallest. Are there other values that work? Right. 9 would work. Now, I can actually include the left endpoint if I go at 9, but the criteria doesn't say that. So I can choose any value that's 8 or bigger, but not 10. Yeah. So A equaling 8 is the smallest value that answers it. But all values that are, greater than or equal to 8, but as we said, less than 10. If A is equal to 10, then we don't have an interval anymore. But it would be continuous from 9.99999 to 10 on the open interval. Okay, so again, not real difficult, but we are answering with intervals for intervals of continuity. Solution sets, essentially, for intervals. All right, part D, do it yourself. Find the smallest value of K so that our function is continuous from K to infinity. Smallest value of K so that it's continuous from K to infinity. Would 15 work? Yeah, but that's not the smallest. 14, 13, what's the smallest? 11, right? 11. So the smallest value of K would be K equals 11. And of course, anything 11 or bigger would work, right? It would be continuous forevermore, but K is the absolute smallest. Find the smallest value so that now it's continuous on the closed interval from K to infinity. Now I want to be able to include the left endpoint. Would it still be 11? Yeah, it has to be greater than 11, right? Because 11 is an open circle on the left endpoint. So to make K as small as possible, it would have to be the very first number to the right of 11, right? On the real number line. What is that number? It does not exist, right? So the values that will work are all values of K greater than 11 for the closed interval. But is there a smallest value? No. So we'll say in this case, no such value. Or DNE. So again, that makes a good multiple choice question. DNE would be an answer choice. There are lots of values that work, and anything greater than 11, you're going to be able to include that left endpoint. But in terms of the smallest one, there is no first number on the number line to the right of 11. So no such value exists. So sometimes we can't answer the question. Okay? And that's good because it's an open circle. If that circle had been filled in, well, definitely now 11 would be the answer, right? Because we can actually reach there. All right, so any questions on that type of stuff? Not too bad. All right, so let's look at this now. Continuity, as you can probably figure out, is a pretty important characteristic of functions. Because if we know a function is continuous, we can start making all kinds of claims about it. That's why we spend a lot of time determining if a function is continuous. But from our previous experiences, we know functions that are continuous either for all real numbers or at least on their domain. So here are some continuous functions that are continuous over their domains. And by domains, I mean like if there's a vertical asymptote that's not in the domain, we won't say it's continuous there. But remember, there are some functions that are not continuous over their domain, like that one. We'll call it x equals c. It's in the domain of the function, but it's not continuous there. So what functions are continuous in their domains? Polynomials, okay? All real numbers. Rational functions, that's a polynomial over a polynomial. Square root functions, cube root functions, they don't exist everywhere for even roots, but they are continuous where they're defined. Trig functions, all of them are continuous over their domains. Sine and cosine are especially interesting because they're continuous where? Everywhere. All your inverse trig functions, especially arctangent, which is continuous for all real numbers. All of your exponential functions, especially e to the x, our parent function, and log functions are continuous over their domain. So the ones with the asterisks are extra important because those are the ones that have domains of all real numbers, and therefore they're continuous for all real numbers. So a type of question that you may be asked is going to require a function to be continuous. We're going to be using theorems. And in order for the theorem to apply, you have to say, you're not going to have to prove, you're going to have to say that the function is continuous. So here's what we could do. We can now start combining continuous functions to create other continuous functions. All right? So on example 4, that's what we're doing. We want to give the intervals for which the following functions are continuous. So we got h of x equals sine of x squared. For what values of x is this function going to be continuous? Well, it's a sine function, right? Sine functions are continuous over their entire domains. So this question comes down to what's the domain of the function? Well, this one should be pretty easy. There's sine of x squared. What types of numbers can we take sine of? We could take sine of positive numbers, right? Those are going to be angles. Can we take sine of negative numbers? Sine of negative pi? Yeah, sine of negative pi is going to work. The domain of sine is all real numbers. We could take sine of any numbers in the whole wide world, positive, negative, or 0. It just so happens that what types of numbers are we going to be taking sine of? Positive numbers or 0 at the very least, right? So I'm going to be able to take sine of all of this. So what's the domain of h? All real numbers. Yeah, sine of positive or 0 is going to work all the time. So the domain of h is all real numbers. There's nothing we can't take the sine of. It just so happens we're only going to be taking sine of positive numbers or 0 at the very least. And because the domain is all real numbers, we could then say that this h of x is continuous. You could say for all real numbers, or if you want to give the interval, how would we say that as an interval? Yeah, negative infinity to infinity. So here's how you could say it. For x epsilon, negative infinity to infinity. There you go. That function's continuous for all real numbers. So all the theorems that we're going to learn that require a function to be continuous, they will apply. We're going to learn the IVT today, hopefully, but there's also going to be an EVT and 2 different MVTs, not MTVs, not VH1s, but MVTs. All right, letter B, h of x. We have a log function that's continuous over its domain, and on the inside we compose it with a cosine function that is continuous for all real numbers. Go ahead on your lonesome. This one's kind of cool, a little interesting. See if you can figure out the domain of this function. That's what it comes down to. If you can figure out the domain of this function, you'll also then know the values for which it's continuous. Hint, what types of numbers can we take logs of? Positive numbers, right? We can only take logs of positive numbers. So if you want to find the domain, you're going to set up your inequality like this, and now you just got to solve it. Remember from pre-cal? What types of inequalities can we solve algebraically? Only linear. And then there's that little thing about flipping the inequality if we multiply or divide by a negative. So we have to solve other inequalities some other way, either by critical values test intervals or graphically. So now that you've gotten that far, see if you can solve that one graphically. Chala, 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 chala. High axis, low axis, high. How you doing? +1. If you keep it equal to 0, you can graph the function cosine x plus 1. If you want to bring the negative one across like some of you are doing, you can then solve that inequality, whereas cosine greater than -1. Either one. Most of y'all are bringing the 1 across, so I'll do that. And so while y'all are sketching Chala, I'll do it too. What the heck. But don't let me get in your way. There's 1, there's -1, Here's 2 pi, right? Pi has 3 pi halves, and 0. Those are your critical values. So it's high axis, low axis, high. There's that. And then -1, if you want to graph it, is going to be this horizontal line. And I want to know where it's strictly greater than -1. Very good. Within one rotation, it's everywhere except at pi. Now notice it has to be strictly greater than -1. So we'll say h is continuous. Instead of listing the interval here, because there's going to be more of them, right? Isn't there another one over here somewhere? Yes. H is continuous for all x. Now this is not listing an interval because the intervals would be infinite. For all x not equal to pi plus, what'd you say, pi n? Yeah, how far apart is the next one? It's one cycle away, which is 2 pi n, right? And remember we say that n is a what type of number? Yeah, it belongs to the integers or the integers. So that should take care of all of them. That's how we listed vertical asymptotes. You find your favorite one and then plus multiples, whole multiples of how far apart they are. So that one is continuous for all those values. And so if you were asked a question about that function and it wasn't like at pi, 3 pi, 5 pi, odd pi's, then you can assume it's going to be continuous there. Okay? So this question could be asked the way I did. What are the values for which it's continuous? But it's the exact same thing as find the domain of the function, which we did a lot in pre-cal. Okay? So make sure you know your parent functions. Make sure you know your unit circle. Okay, let's get to the IVT. Maybe we finish this section today, maybe we don't. The IVT is the first of several VT theorems we're going to have. This one is called the intermediate value theorem. Intermediate kind of implies what? In between, right? Kind of like the squeeze theorem or sandwich theorem, but that one implied in between smushing it. This one doesn't necessarily imply smushing or smashing, but it does imply in between. And then for value, you could substitute or add little y in there. So it's an intermediate y value theorem. Okay, and because it's a y value, you can think of IVT as the abbreviation for intermediate value theorem. And you know what else has the I sound as an IVT? Y, Y, I, Y, Y, I, Y, I, Y, right sign, Y, I. There you go. So as we go throughout the year, I might actually slip and call it the YVT, but it's really just the IVT. But it's going to guarantee the existence of an intermediate Y value, okay? Let's read it. I think you'll be impressed with what this theorem says. Again, there's two parts. There's the if part, which is the hypothesis, and then there's the then part, which is the conclusion. And of course, if the if part is true, then the then part follows automatically. If a function y equals f of x is continuous on some closed interval, and we'll define that to be a, b with a bracket, okay? A is less than b. So from a to b inclusive. That's what we've been looking at, continuous on a closed interval. So it's going to look something like this, right? No holes, jumps, or gaps in between a and b. And then, of course, the function values are at the endpoints. That's it. That's the only thing we need. If a function is continuous on a closed interval, then here's what we can say. Then the function f takes on every single value, and by that we mean y value, between f of a and f of b. What are f of a and f of b? Those are just the y values where? At the starting point and end point. Then the function will take on every y value between the y values of the endpoints on that x interval. Put differently, oh yeah, I want to hear it differently. If we know a specific y value, say y equals not me, but y equals you, and we know that that y value resides between the y values of the endpoints, then the theorem also guarantees at least one x value between the endpoints, or possibly an endpoint, where the function value equals that y value. Here's what it means graphically. Let's say we have the blue function, f of x, and we're going from orange A to orange B. The blue graph, you eyeball it, is it continuous on the closed interval? Yeah, okay. So f of a is going to be down here. Here's the y value on the left, call it f of a. Here's the y value on the right. Basically, what we're saying is as this graph moves from left to right, it's going to have to go from this y value down here to this y value up here through a continuum, right? And there's no way to get from this y value down here to that y value up there through a continuum without passing through all the y values in between those two values, at least what? At least once, okay? So if you notice this blue graph, it does pass through all the y values. Now notice it dips outside. It could dip above the top two. We don't know that. There's no guarantee. But we do know that to get from the bottom y value to the top y value, or it could be flipped. We could start higher than lower. There's no way to get from one y value to another y value through a continuum without passing through every y value in between at least once. So when we state it a little bit differently, here's where we can use it to prove a y value. If we have a given y value, called it u, and we know it lives somewhere between f of a and f of b, the theorem says then that there's going to be a guarantee of at least one x value strictly or between a and b that's going to generate that function value. There might be more than one. Like if I pick this y value here, there's 1, 2, 3 points of intersection. There's 3 x values that generate it. But the theorem is going to guarantee one of them. Okay? So if you think about it, it's kind of a no-dub theorem. I can't get from one point to another point through a continuum without passing through everything in between, right? I can't get from here to the door without passing through all the physical space in between. Now, I can kind of take a detour and go around, but I'm going to physically pass through everything in between, which gives a new punchline to the age-old joke. Speaking of chicken, one-stroke chicken. Why did the chicken cross the road? He had to. There was no other option. He could not teleport, right? That's why he had to cross the road. By the IVT, there was no other way to get to the other side but for to cross it. He could not teleport. That's pretty funny. Tell that to your math friends and see if they're still your friend afterwards. Okay? All right. That's the IVT. It's a no-duh theorem. Okay. Real quickly, we're just going to kind of give you an example to kind of make you understand what this theorem is, because it's pretty important, but it makes sense, right? If you measure the outdoor temperature on your back porch to be 47 degrees Fahrenheit one morning at 8:15 a.m., oh, man, I can't wait for that. Can you? That is, man, get here, please. And I guess it must be a weekend, because hopefully you're at school by 8:15, right, because y'all are achievers. It's 47 degrees on the back porch. You go out there 4 hours later, so it must be a weekend, right? And now 4 hours later, same back porch, same spot, you measure the temperature to be 62 degrees Fahrenheit, right? Explain then why there must be some time during the day between your readings at 8:15 and 12:15 where the temperature on your back porch on that day had to be exactly, precisely 51.351 degrees Fahrenheit. Why? We weren't there to experience it, but in a court of law, you could prove that it had to be that temperature on the back porch at least once during that time interval. Why? What's our function? Temperature? What do we know about temperatures? Do they increase and decrease through a continuum, or do they jump? They can increase rapidly, very fast, very slowly, but they also do so through a continuum. So because temperatures increase and decrease through a continuum, and because, here's the important thing, the y value we're trying to prove, 51.351, falls where in relation to the two readings? In between. It's an intermediate y value. Okay, so we would set up an inequality. Basically, we'd say since 47 is less than 51.351, which is less than 62, since temperatures increase and decrease through a continuum, by the IVT. We're going to throw that in there, okay? By the IVT. That gives our argument credence, right? And weight. By the IVT, there had to be at least one time during the day between 8:15 and 12:15 where the back porch temperature was in punto exactly 51.351 degrees Fahrenheit. Now, do we know what time during that 4-hour span that it was that temperature? No, okay? So the IVT is what's called an existence theorem. It tells you that something exists, but it doesn't necessarily tell you where it exists. But for some, that might be all they need. right? They don't need to see to believe. They just need to believe, right? Sometimes you don't get to see it. You just know it exists. And it's because of the IVT. So it's a pretty no-duh theorem. We take it for granted sometimes, but it's actually a very, very important theorem, okay? So we'll stop right there, and we'll look at an actual math example, piecewise fun, starting tomorrow. Oh, boy. Remember, the homeworks are out there, the worksheets are out there. You should be doing them even though you never turn them in.